Have you ever looked up at a small plane buzzing overhead and just wondered, what is going on inside that engine? It's this incredible symphony of controlled explosions and pure mechanical genius. And today, we're going to trace that entire power chain from start to finish.
And that's the big question, isn't it? How does this thing do it? Well, it's not just one magic component. It's a whole series of events, a chain, where every single link is absolutely critical to turning liquid fuel into the force that literally conquers gravity.
So here's how we're going to break it down. We're going to follow that power chain all the way through. We'll start with the 4 breaths every engine has to take. Then we'll see how propellers are basically just wings that spin. After that, we'll look at the engine's very specific diet. And finally, we'll see how these planes cope with trying to make power in thin air.
Okay, so let's start at the heart of it all, the reciprocating engine. It's a true marvel, and it runs on this beautiful, simple, and repeating 4-part rhythm. It's called the 4-stroke cycle.
Step 1 is the intake stroke. You can think of it like the engine taking a deep breath. A valve pops open, the piston moves down, and it sucks in this perfectly mixed vapor of fuel and air. The cylinder is now loaded and ready.
Next up, we squeeze. That valve slams shut, and the piston shoots back up, compressing all that fuel and air into a teeny tiny space. And this is key, because the more you compress it, the more powerful the explosion is going to be.
And here it is, the bang. This is the moment we've been waiting for. A spark plug fires, igniting that super compressed mixture. It creates this massive, controlled explosion that violently shoves the piston back down. Now, what's incredible is that this is the only one of the 4 strokes that actually creates any power. This is where chemical energy becomes the mechanical force that spins the whole engine.
And finally, the engine has to exhale. The exhaust valve opens up. The piston comes back up one last time, and it pushes all those used, burnt gases out of the way. And just like that, the cylinder is clean and it's ready to start that whole dance all over again. Remember, this is happening hundreds of times every single minute in every single cylinder.
So all those little explosions are now spinning a crankshaft with a ton of force. But how do you turn that spinning motion into forward motion that pulls a plane through the sky? Well, that's where the propeller comes in.
You know, the easiest way to wrap your head around a propeller is to just think of it as a wing. A normal wing on a plane is an airfoil, right? It's shaped to create an upward force called lift. Well, a propeller is the exact same thing, an airfoil, but we stand it up vertically and spin it around. Instead of creating lift, it creates a forward force we call thrust.
And this right here really drives the point home. A propeller isn't just some simple fan blade. Oh no, it's a really complex aerodynamic surface. It has to deal with all the same stuff a wing does, drag, stalls, you name it. It's designed to bite into the air in a very specific way. So if you've ever gotten a close look at a propeller, you've probably noticed it's not flat. It's got this really obvious twist to it, from the center all the way out to the tip. So what's up with that? Why the twist?
Well, this chart explains everything. Think about it. In one rotation, the tip of the blade has to travel a huge circle, but the part near the center, the hub, travels a much smaller circle. For them both to finish at the same time, the tip has to be moving at an absolutely incredible speed. We're talking almost 400 knots here, while the hub is moving way, way slower. So that twist, that's the genius solution to the speed problem. The twist actually changes the blade's angle to the wind along its entire length. This makes sure that every single part of the propeller, from that slow-moving hub to the screaming fast tip, is creating the same uniform amount of thrust. It's just a beautiful piece of engineering.
All right, we've got the power from the engine, and we've got the propeller creating thrust. But that engine is a picky eater. It needs a very specific diet to keep running. So let's look at the system that actually feeds it.
For a lot of these planes, that job falls to the carburetor. It's this really clever mechanical device. It takes air from the outside, squeezes it through a narrow throat called a venturi, and when you squeeze air like that, it speeds up and its pressure drops. That little area of low pressure then acts like a vacuum, sucking a fine mist of fuel into the air. Boom, you've got a perfect combustible mixture. But there's a really dangerous side effect to this simple process. That pressure drop causes cooling, and when the fuel vaporizes, that causes cooling too. Together, they can create a sudden, massive drop in temperature right in the engine's throat. It's kind of like instant frostbite that can choke off the air and just kill the engine. And I'm not kidding, the cooling effect is staggering. The temperature inside that little carburetor can plummet by as much as 70 degrees Fahrenheit. Now think about that.
This means, and this is what's so wild, you can get deadly carburetor ice on a hot, sticky, 100-degree summer day. It can happen when you least expect it.
And this is exactly why pilots are trained to be paranoid about it. They're always on the lookout for the signs. A little loss of engine RPM, some engine roughness. These are the first whispers of a major in-flight emergency that you have to handle right away.
Okay, on to the final link in our power chain. The engine's running great, the propeller's pulling hard, the fuel is mixed perfectly. But what happens when the very air the plane needs to fly becomes the problem? It's one of the classic challenges of aviation, right? As a plane climbs higher and higher, the engine feels weaker and weaker. Why is that?
The answer is really simple. The engine can't breathe. Just like a mountain climber gasps for air on Everest, a normal engine gets starved of oxygen. The air is just less dense up there, so every breath the engine takes has fewer oxygen molecules in it, and less oxygen means less power.
So, engineers came up with an amazing solution, the turbocharger. You can think of it as an air compressor for the engine. It basically creates sea-level air on demand, forcing dense, oxygen-rich air into the engine even when it's flying tens of thousands of feet in the sky.
And the way it works is pure genius, because it recycles waste energy. Instead of just dumping hot exhaust out, the engine uses that exhaust to spin a turbine wheel at insane speeds. That turbine is connected to a compressor, which grabs the thin outside air, squeezes it down, and then shoves that now dense air right back into the engine. It's a brilliant, self-powering loop that turns useless exhaust into raw power.
So, there you have it, from that four-stroke dance inside the cylinder, to the twisted wing of the propeller, to the systems that feed it fuel and even compress the air, the piston engine is this intricate, powerful, and amazing machine. It's the technology that powered the entire golden age of aviation. But as we look to the future, it makes you wonder, doesn't it? What kind of power chain is going to define the next one?